friends, today we will see how to check the results. So already we have completed the modeling and we have done the analysis. Sorry, we have to run the batch run. So once we complete the model, we need to check all the inputs and load cases has to be built, and then do the batch run. So once the batch run is complete, it will come to this page. Okay, this is output window, static output processor. Okay. So here you can see in the left side load case analyzed, and here standard reports and general computed results. Okay, in this case. So first we will see what are the things to be checked in the output. Okay, first we need to check the stresses. Okay, stresses. So why stresses are developed? Because of the fluid flow because of the fluid flow and because of the temperature, whether there is an expansion or contraction will be there. So based on that, stresses will be calculated. So there are different stresses will be acting, like axial stress, bending stress, torsional stress. So a lot of stresses will be there, but we need to check as per the codes and standards. Okay. So if you select ASME B31.3, then the stresses has been calculated for different load cases. Whatever load cases we have built, for those load cases, stresses will be calculated against the formula provided in ASME B31.3. Okay. So in ASME B31.3, for first we will check the case Hydrotest case. So in Hydrotest case, you just go to Hydro here, load case 1, and you select stress summary. Stresses you can check anything. Stresses extended, stress summary, and code complaints. Okay. So first I will check the stress summary. I will show what is the result, and then weave report. Select here and weave report. Okay, this is Hydrotest case. The stresses developed for Hydrotest. Okay, during Hydrotest, what will be the stress range? Okay, so here you see the ratio it is given. Ratio is 10.1. So this ratio only you have to check. Okay, WW plus HV is the hydro pressure. So based on the hydro pressure, stresses has been calculated, and based on the fluid weight. Okay, whatever fluid inside, based on the fluid density, the stresses has been calculated. What is stress? Stress is load by unit area. Okay. So your ratio is 10.1%. Okay. So how this stress ratio has been calculated? What is stress ratio here? Stress ratio is nothing but code stress divided by allowable stress. Okay. So this is stress ratio is code stress divided by allowable stress. So in this case, what is your code stress? So code stress is 17.3. Okay. So our code stress is 17.3. And what is your allowable stress? 172.4. So 17.3 divided by 172.4, we'll get 10.02 into 100 for ratio 10.03. So stress ratio is 10.03. So it is 10.1. So it is approximately correct. Okay. So it has been calculated based on the code formulas provided in the code. For example, in the Hydrotest case, what is the formula means? SL should be lesser than 0.9 of SY. Okay, so this has been taken from ASME B31.3. Okay, what is SL? SL has been calculated based on this one. SL is code stress, nothing but SL is code stress, and SO is code stress is longitudinal stress. Here in this case it is longitudinal stress. And what is SO? SO is yield strength of the material. Okay, the yield strength of the material you can check in our input. These are if you go to input spreadsheet, you will get the value, or you can take the value from ASME B31.3 or a section 2 PART-3. Okay, so here you see at note number 10, the SY is no, this is SY 172.375. That means 172.4. It has been rounded off. So hydrotest case, select stress summary. Okay, so allowable stress is 172.4. This has been taken from ASME B31.3. If you select 31.3, you will get the yield stress. If you have some other material, for example 106 grade B, then your yield strength will be varied. Okay, so based on the material, the yield strength value will be varied. Okay, and you have to select the particular code. Okay, so now we will see the other result. Okay, now I change the material again. Okay, so as per code, it is, 90% is allowed. I mean, as per code, it is, you can leave up to 50 to 60. As per code, it is 90%. Up to below 90% means it is considered as qualified. But as a good engineering practice, or so based on the experience, whatever lead engineers used to tell, means you have to maintain 50 to 60% for the hydrotest case as well as for sustain case. Okay, because this is sometimes if they do some mistakes at the site, for example, if they not provided the support as per our stress requirement, then sometimes the stresses will be increased. Okay, so for that purpose, what we will do, we used to maintain 50 to 60%. This is we'll call it as good engineering practice. Okay, this is for sustain case, sorry, hydro case as well as for the sustain case. So I will show you in 31.3 you can take the value. If you go to 31.3, what is the table? Basic allowable stress. This is table A1. I think in the slide itself we have, yeah, this is table A1, and for this material, what is our material? A312 TP316L. Even yield strength is 25. Or if you go to ASME 31.3 directly, you have to check the material. Say A312 TP316, and so what is the temperature? This is allowable stress value, and 25 is your, 25 is your yield strength, because this is yield strength. So yield strength in KSI. Okay, so you have to convert that yield strength. You need to convert. So using converter you can convert, or in the Google you can search. So pressure in KSI, it is 25 KSI. So 25 KSI means 172.368 megapascal. Okay, it is, the unit is in megapascal. Here is it, unit is in megapascal. So it is, if you convert, you will get this value. Okay, so either you can take the value from 31.3 or from Caesar input itself. This is just giving an idea how it has been calculated, this test. For SL, if you want to check the SL, then you have to calculate as per this formula. If you want to calculate SL, you have to consider as per the formula. Means SA is axial stress plus bending stress and torsional stress. Okay, square root of SA plus SB the whole square plus 2ST square. Okay, so if you calculate based on this, you will get the value of SL. So here, what is SL? SL is 17.3 megapascal. You will get this value. Okay, so you can try this one. Okay. So this is SL, and this is from the code. So if you want to get the formula, you can check the code, or if you go to Caesar, in Caesar help menu also, you will get this one. 1 minute, I will show you that one. Okay, so here I am closing this. In Caesar, here go to help and you go to quick reference gate. Select quick reference gate. So this is a quick reference gate. So in this you will get all the details. So if you type 31.3, just I'm telling, if you type 31.3, yeah. So you see. So what as per 31.3 for sustain, for hydro they have not given. For sustain, sorry. For sustain they are given SL should be lesser than SH. And what is SL? SL it is given IA SLP plus FA FAX by A AP plus SB square. That is nothing but axial force. SA, this is SA, okay. SA plus SB the whole square. The same formula what is available in code. This is from the code. This is from the code ASME B31.3 302.3.5. Okay. So if you go to this page, you will get this formula, this equation 33A. Okay. Or in the Caesar, so this is for hydrotest case. Then we'll see the sustained stress case. What is the formula and how it has been calculated. So go to sustain. For sustain case, what are all the load cases you have to select? You have to select all the sustain cases like all sustain, all sustain, and alternate sustain case and sustain case. Okay, you have to select like this. So before that, I will tell you what is this stresses extended, stress summary code complaints. So all it will give the stress results only, means stress ratio, okay, of the particular load cases. Okay, in stresses, what it will show, you see, in hydro, for example, if you take hydro, so in stresses you can see a lot of SLP. How this SLP means this value. This value, this SLP is there. No, this is the one is directly calculated. So you can calculate yourself. SLP means maximum. If you double click the ratio, it will show the minimum value, and again if you double click, it will show the maximum value at the top. It will be in the descending order. Okay. So now we will see our SLP is 3. Okay, and what is SB bending stress? So our bending stress is 15.3. Okay, you can calculate like this, and your torsional ST, torsional stress. So your torsional stress is 0.3. So you can calculate according to this also. Okay. So in stresses, it will show all the values like based on the formula. It will show all the stresses values. Okay, and then allowable stress, code stress, and then ratio. If you go to stresses extended, so in stresses extended, you can see axial stress, bending stress, again torsional stress, hoop stress, maximum stress intensity, and again same thing. Only thing, this piping code has been included here. Okay, so all will show the same results only. The maximum result is this one: highest stress ratio, core stress check pass, highest stress ratio, and core stress, maximum stress intensity. Up to this, it will show. In stress summary, it will show only this value. If you check here, if you go to stress summary, it will show only the maximum value. So if you want to see the stresses in all the nodes, then you can go to stresses or stresses extended. Okay. So in stress summary, see, it is having it will show only the maximum value. Then go to code complaints. Again, code complaints, it will show all the values for all the nodes, like stress ratio. You see code stress, allowable stress, and ratio. It will show from to 2. For example, we have started our model from 10 to 20. So it will show from 10 to 20, or you see from 10 to 30. Here we have started model from 10 to 30. So at node number 10, what is your value? What is your code stress and what is your allowable stress? Okay, same thing only. So any one you can check. For example, if you are going to check, if you are some experienced person, then they will select all the cases. Okay, whatever load cases they want, just select stress summary and they will see the result. So wherever failure is there you have to go to check the stresses or stresses extended to find out the node numbers. What are all the node numbers it is having failure? Okay. So here I say in this itself you can find out the maximum stresses. So this is enough. So it will show the maximum stress at node number 5020, means 10.1% at 5020. That means for other node numbers it will have lesser than 10.1%. Okay. So anything you can check, but first you follow stress summary. Then if any failure is there, you go to stresses to find out the failure node numbers. Okay. Then go to the sustain. Now we are going to check the sustain cases. I will show you one example for sustain. Stress summary. So you see in sustain, what is your ratio? 14.5%. Okay, 14.5. And what is core stress? 16.5. And your allowable stress is 115.1. So for I will show you. 16.7 is your core stress. What is stress ratio? Core stress by allowable stress. So 16.7 divided by 115.1 into 100. So what is your value? 14.5. You can see. So you will get 14.5%. So it is well within the allowable. Okay. So what code says? As per code, SL should be lesser than H. For sustain, this is a formula. For sustain strength, SL should be lesser than SH. What is SL? SL is longitudinal stress and SH is hot allowable stress. Okay. So this longitudinal stress is having the same formula, this one. So you can calculate based on this formula, this longitudinal stress, and this SH value, you can take it from ASME B31.3 or in the Caesar input spreadsheet. You can find, see, SH1, SH2, SH3 up to SH9. That means hot allowable stress for temperature 1, hot allowable stress for temperature 2. So up to hot allowable stress temperature 9. Okay. But in this case, how many temperature we are given? You see in the left side, we have 5 temperatures. In this case, we have used 5 temperatures. Means first is for maximum design, second is for maximum operating, third is for minimum design, and T4 and T5 for pump working standby temperatures. Okay, so how this value has been obtained means you have to go to 31.3, you will get those values. For example, the same thing, see, in table A1, basic allowable stress, this is the allowable stress value. And for this material, our material is A312 TP316. And what is our temperature? Our temperature is 82. Okay. So here, so the temperature here it is given as degree Fahrenheit. So our degree Celsius. So you need to change it as centigrade to Fahrenheit. Means 82 degrees centigrade to Fahrenheit is 180. Okay. So 180 means it should be from year to year. So for 100 degree it is 16.7, and for 200 degree also it is 16.7. So up to 300 degree Fahrenheit, your allowable stress value didn't change. Okay. So up to 300 degrees, say 300 degree Fahrenheit. Okay. That means degree Fahrenheit, 148.9 means up to 150 degree there is no change in temperature. I mean allowable stress value. So you can check like this here also. Here you can check. For example, 149. So there is no, I mean there is a mild change. You see, for 148.8, 148 point, sorry. Or you can take 147. So 147, the same allowable stress is there. Okay, that is, think about 16.7 KSI. So you can check the stress value 16.7, and our unit is in megapascal, 115.142. Okay. So up to 147 there is no change. If you go to 148, there is no change. So where from which temperature onwards there is a change in allowable stress? 148.9. So above that it is you see that is 149. From 149 it is getting changed. Yeah, you see. So if the temperature increases, your allowable stress value will be reduced. You have to note out this point, because if you are having more temperature, then your allowable stress value will be reduced. That means for your stresses will be increased. Okay. Understood? No, because allowable stress, if allowable stress is more, then you can easily qualify. For example, if your allowable stress is 115.1 and your code stress is 16.7, so 16.7 divided by 115.1, you'll get 14%. Okay, so if your allowable stress value has been reduced, for example 100, so your what is your stress ratio? 16.7. It has been increased. Okay, so if temperature increases, your allowable stress value will be reduced, so that our stress ratio also will be increased. Okay, this is for expansion case I am telling. In sustained case, it will take the maximum hot allowable stress value, not minimum allowable stress, maximum allowable stress value only it will be considered. Okay. So you see it is 115.1. It is SL should be lesser than SS. That means if the stress ratio is below 100, then the strain stress is okay. Okay, in our case, stresses are well within the allowable, because our stress ratio is 14.5% only. Okay, so here also as a good engineering practice, we need to limit the stress within 50 to 60%. Okay, this is very important for the sustained case. Okay, so I 1 minute. So we have checked the stresses in sustained case. Then we need to check all the sustained case, not only this sustained, all the alternate sustained case. So you need to check the stress summary. Just check the stress summary, that is enough. So all the stress ratio are okay. So why we need to check all the alternate sustained and sustained cases? This alternate sustained is applicable for temperature T1. Okay, if any pipe lift off is there, then the stresses will increase. Okay, so in order to avoid the pipe lift off or in order to check the hot sustain, we are doing this one. I mean, they have included this alternate sustain case in the analysis. Okay, so next we will see first hydrotest stresses we have checked, that is fine. Then sustained cases we have checked, the results are okay. Then we are going to check the next stresses in occasional cases. So occasional cases in our model, what we have done, we have considered uniform loads, that is seismic loads or earthquake loads. This acceleration we have values we have considered. Okay, seismic coefficient value we have considered, and for the winds, I mean another occasional cases, wind load cases. So in wind we have considered different loads, means pressure versus elevation or AAC 7, like that we have considered. So for those cases we need to check the stresses. Okay, so for this case, for this occasional, you have to select all the occasional cases. We'll see. You have to select all the occasional cases and select stress summary and view reports. So in occasional cases, you see the stress ratio is 3.8% for load case number 24. That is a maximum stress. That is okay. And here also 3.8 and 1.9, 2.2, 6.1, 6.3. If the, you see, first you need to check code stress check past. Okay. So it will show the maximum value for individual cases. All are passed only, you see. 12.3, 16.1, 12.6, 12.6, like that. Okay. So all stresses are okay. I mean, code stress for the occasional load cases, all the cases, stresses for all the cases are within the allowable limits. So you can you need to find the difference. So when which are all the cases to be checked? You can check all the cases, but the worst case will be the combination with sustained case. Wherever we have combined sustained case plus wind, sustained case plus seismic, those cases only we need to select and check the stress summary, because it will show the maximum stress value for this case only. This will be the worst case. For example, we will see the difference. Okay, take load case number 24, L12 minus L2. What is L12? It is wind 1. Wind 1 means wind acting in plus x direction. Okay, so wind is acting in plus x direction. So you can check, this is an individual case. L12 minus L2 means W plus T1 plus P1 plus wind 1 minus W plus T1 plus wind P1. So if you subtract this one, you will get only wind 1. Okay. So if you check the stresses for load case number 24, it is in plus x direction. So stress ratio is 3.8 only. So stress ratio is 3.8. Okay. Then in the same x direction, we are combining with with sustain. That means L24 plus L22. L24 is wind 1, okay, and L22 is sustain. Means W plus P1 plus wind 1, okay. So we can check the stress summary. So here you see 13.7. So there is a huge difference. I mean 10% difference is there. So in only wind case you will get 3.8%, but with the combination of sustain case you are getting the maximum value 13.7. So I mean you can check the stresses for the pure occasional, but the worst case is occasional plus sustain. Okay, so you can, if you check, if the stresses are okay for these cases, then automatically this stresses are qualified for the other cases. Okay, so what I am trying to say is, in order instead of checking all these cases, you can check only these cases with the combination of sustain case. Okay, that's what I am saying. So for example, you take any load cases and check stress summary and wave reports. So now we will see as per code what is the formula and how it has been calculated. Okay. So what is our code stress? Stress ratio is 13.7. Code stress is 21% and allowable stress is 153.1 into 100. See 13.7%. You'll get 13.7. So how this has been calculated. So if you go to code, or if you want to see the code, you can see the code also. When these screenshots and all, I took it from the code only. Okay, stresses due to sustained loads, and these formulas and all, I took it from the code. Okay, so everything is available in the code. And I will tell you how to qualify the stresses. First we'll see how it has been calculated, then we'll see how to qualify the stresses in sustained case, occasional case, expansion. Okay, so mostly you will not find any failure on the hydrotest case. If it is passed in sustained case, it will automatically qualify in hydrotest case. Okay, if you do any mistakes on the input, then only you will get the failure for hydrotest case. Okay, so here for occasional cases, see, for occasional cases the same, the formula is applicable. This SL should be lesser than 1.33 of SH. Okay, SL is same only, longitudinal stress, and SH is minimum, not minimum, out allowable stress. Okay. Not minimum, it is hot allowable stress. I will show you the results. Okay. So here SL is using the same formula. SL is nothing but code stress in this case, and SH is allowable stress. For us code stress and allowable stress is common, but based on the cases the values will change. Okay. So here SL is calculated like this, and SHs will consider from 31.3 or Caesar input spreadsheet. Like same thing what we did for occasional case. This is 115.13. Sorry. So I will change the temperature. Now I will change the temperature. I will show you the results. Maybe results may change. Okay, so this all allowable stress, you can take it from 31.3 that I already have shown. So what is the difference between sustain and this occasional case means? Only thing, this 1.33 only, it is 1.33 times of allowable stress, hot allowable stress. So your normal hot allowable stress is 115.1. Correct now? From the spread input, you'll get the value. See, 115.146 is your hot allowable stress. And for occasional, what we need to do, we need to multiply with 1.33. That is 115.146 into 1.33. Sorry, 115.146 to 1.33. So you see your allowable stress will be 115.144. You can see 153.1. Okay. So like this only it has been calculated. So you can. So no need to update this one. I mean, in the load cases, you will have all the details. Okay. I will show. So first we'll see the stresses. Here also the same thing. SL should be lesser than 1.33 of SH, or SL by 1.33 of SH should be lesser than or equal to 1. That means your stress ratio should be below 100%. If it is below 100%, it is okay as per the code. But as a good engineering practice, we need to limit the stress below 90%. That is yeah, you can maintain 90% or 80% or 70%. Anything is okay. But up to 90% we can allow for occasional cases. Okay. So occasional cases means we'll have wind, seismic or snow loads or accidental load cases. Blast also will be considered as an occasional. Okay. So now we'll see means in the load case editor, if you go to load case editor, you can see for the occasional cases, here you see 1.33. Occasional load factor has been added, and okay. If you leave blank also, nothing will happen. For example, just I am leaving blank in this case. I will show you the result. We'll see if any changes is there or not. So this is as per the code. You see in the code it is given as limits of calculated stresses due to occasional loads. Stresses produced by occasional loads such as wind or earthquake may be as much as 1.33 times of basic allowable stress given in appendix A, that is table A1, from table A1. Nothing but this table only, this allowable stress value. Okay. Now we'll see the result if any changes are there. See, allowable stress value remains same only. If you keep that column as blank, then it will then also default value will be considered. Default means as per code. As per code, what is applicable? It is 1.33 of SH. So it will be calculated based on the code only. If you're giving 1.33 as occasional load factor, or if you're leaving as blank also, not an issue. Okay. So I left those. You see, I left this occasional load factor as blank, so it has calculated based on the formula, based on the code. Okay. So this is for occasional cases. Okay. Now we will see why the failure will happen for mainly for the hydro and sustain case. Next we will see the expansion case. Expansion, maybe it will take some time. So first we will see the failure case. Why the failure may happen for the sustain and hydrotest case. First thing is if you're making any mistake on the inputs. For example, for this instead of pressure it is in bar. Okay, if you are entering instead of one some wrong input, if you provide so for example 15 or 15 means it will the stresses will be more, but it will not show any failure. Okay, I will just enter some random value 100 bar. This much mistake nobody will do, but just I am showing you. Okay, so what will have impact if you provide wrong input. Okay, so I will just run the system. Okay, we'll see in sustain what is the impact. See, stresses has been increased, but it's a very less impact. Means previously how much it was around 14% or something, no? In sustain case. What is the percentage? Yeah, 14.5% it was there. Now the stresses has been increased to 48.6 only. It is having less impact in this case, but if we, this is wrong only, no, whatever value it is getting, this is wrong. Okay, I will show you some other mistakes. If you do some mistake, it will have an impact on the stresses output. So for if it is under body, just make it as 1 only. Make it as some 40 bar. And if you reduce the thickness, instead of schedule 40, give schedule 10s. It's stainless steel, just give 10s. 3.406. Okay. Okay, so just run the system. And we'll see the result. You see again stresses has been increased only, but it is not showing any failure. Okay, so in this system maybe they are designed like that. Okay, so based on the pressure and thickness value only, your stresses will have impact for the sustain and hydrotest case. Okay, because WW plus HP for hydrotest case and W plus P1 is for sustain case. So main thing is pressure as well as the thickness value and the fluid density. Okay, if you enter wrongly, for example, this unit 1105 instead of 1105, 11050, someone entered wrong value, we'll see the impact. You can edit here also. Just I am saying fluid density at all direction. For all the node numbers, and pressure also 6 bar. This is for discharge line. Okay, just I am giving 40 bar, and pressure is set. Okay, thickness will keep it like that. Just I will show if any changes are there. You see there is an increase in stress ratio, no? because initially it was very low, 14.5%, but once you are changing the inputs, the output is changed. But still there is no failure. But you can see the failure is observed in a case, expansion case. I will show you that one. You see the stresses has been increased 72.9%. Okay, maybe this system is having a good support, good support, as well as the thickness has been designed for higher pressure. The thickness has been calculated for the higher pressure. Okay, now we will see. I mean, why the failure would happen for a sustained case is, one is incorrect inputs like pressure and thickness or no, fluid density. Okay, any value or any units, if you are doing wrong thing, then it will show failure. Okay. So then one more important thing is insufficient support. For example, if you don't have support here, or if somebody is not following as per support span. Okay, just I am removing the support. We'll see the result at this portion. Okay. Now you see, you can see, so wherever it is showing red color, that means the stresses are exceeding the allowable limit. Okay, so you see in occasion also it is having failure. So if you don't have proper support, then you can see how the failure is happening for in all cases. Sustain, if you check the stresses, you check the stress summary. So it is showing failure at 430. Okay, maximum is 123.6% at node number 430. Okay, so if you want to see any other nodes or failing, go to stresses. Now only you have to go to stresses. Once you find stresses are exceeding the limit, okay, then you have to find what are all the nodes the stresses are failing. Okay, so you go to stresses, view report, and double click this ratio. Double click this ratio again, double click. You see, so there are different nodes at node number 430 and node number 1130. Again, it is getting repeated. Okay, you see the stresses has been increased 98 up to 90. So what we'll do, we need to limit the stresses for up to 60. Like this, you need to select and in the notepad, just you copy and paste it at the notepad. Okay, or if you want to see on the animation or on the image, just go to 3D plot. Here it is there, no? So this button, red color button, is view animation. It will show the animated view, how the pipes are behaving on the simulation, how it is the pipes are moving. Okay, it will show that one. I will show you. First we will see the 3D plot. Here is the 3D plot. Go to 3D plot. In 3D plot you have to select the sustained case. So I mean we have failure at the sustained case. No, go to 22. Select sustained case. Now, so you see a lot of buttons were there. In this we can see one by one. We'll see. First, now we are checking only the stresses. Means you have to check this overstress point. Here it is there. No, this is overstress point. You select this. In the left side you can see level 6% 100 means greater than 100%. Wherever it is showing red color, there 100%, the stresses are more than 100%. Okay, so wherever you are having this color, the stresses are more than 80%. Okay, so now we will focus only on the red color, that is 100% or more stresses. Okay, first we need to qualify the stresses as per the code. Okay, once you qualify the stresses as per the code, then we will go to, we'll limit the stresses as a good engineering practice. We will limit the stresses up to 60% if it is possible. If it is not possible, then you can limit the stresses up to 70 or 80 based on the I mean, it will depends on the case to case only. Okay. So now see where is our red color? Yeah, you see. The main failure is at this location, here and here. Because what we have done, we have removed the supports here. So this is like reverse engineering I went, means in order to show you how the failure may happen. Okay. So here you see the failure is here. Here and here. Okay. And you can see the deflection, how the pipe is behaving here. The left, you see deflected shape. The deflected shape you can find. You see. So you can see the pipe is moving downwards because there is no proper support. Because two valves are there. If there is no support, means what happened? The pipe automatically will go down. So you need to add supports in order to qualify the stresses. Okay. And if you want to see that grow means it will show slowly how it is happened. The deflected shape only, but it will show gradually, one to one layer by layer it will show. Okay, so this is, so you can find like this also. Okay, so one more thing also you can find, it means based on the displacement. I will tell you while checking the displacement. So what is the deflection? You see, this is a deflected. So this is a deflection or sagging. We will call it as sagging. Okay. So this is the deflection shape of the pipe. Deflected shape of the pipe. So if you check the displacement at this point, and you will see here also, here itself you can check sustain. This is a maximum force, maximum in XY direction, and maximum moment XYZ direction, and displacement XYZ. Now if you check the displacement in Y direction, see maximum displacement at this node number, that is 3.9 mm only 3.9 mm. Okay. So as per stress design basis, you can go up to 12 mm also. Okay, but in 3.9 mm itself it is showing failure, means because there is no proper support. Okay. So this is a deflected shape. So if we enter like this, you will get the next maximum displacement. Okay, just press enter. Just tap enter means you will get all the displacement value in dy. Okay. So like this you can find out the node numbers. Now we find out the location where the failure happened, here and here. So now I am going to, in occasion also it was showing failure, you see, L28, because of sustain only it is showing failure. You can see here L38, L39, L40, L41, the same cases like this, L30, because L28 plus, sorry, L28, L29, L30, L31. You see, pure occasional case, it is the stresses are okay, but when you combine with the case sustain, it is showing failure because in sustain itself failure is there. Understood? No. So now we need to we'll add the support and we'll see the result. So in mainly in hydro, occasional and sustain supports are very important. So you need to add support as per the span. But in the pipe support center, the span is provided only for the straight pipes. So if any valves or in between any strainers or any other elements, rigid elements are coming, then that span is not applicable. So you need to provide the support as per your experience or as per your guidance from your lead engineer. Okay. So already we've added. We'll add the support. So once you add the support, we'll see the result. So already we saw the results, no? So and the inputs what we have changed, no, that is also having an impact. Okay. So you see the causes of failure means failure is due to incorrect inputs like pressure, pipe wall thickness, fluid density, etc., and inadequate or improper supports. Okay. So how to qualify the stresses means in hydro unsustained addition or relocation of support, correct the mistakes of wrong inputs and okay, wrong inputs. And now you see in the expansion node it is showing failure. So in occasional case, while the failure happens, generally in some cases, for example, if a pipe is running very lengthy lines, okay, 1 minute, like pipe rack, okay, if a line is running like this, okay, so some people what they will do, they will provide all rest support. They will not use to give rest plus guides or limit stop. So if they don't have enough guide supports, it may failure in occasional case. Okay, especially when the line is running above 10 meters because wind is applicable above 10 meters only. Some cases there will be a failure in earthquake. If you have high earthquake values, seismic values, if the site is in zone 4 or zone 5, then you will have high seismic coefficient value, for example 0.5, 0.4 like that. So in those cases, this horizontal restraints are very important, like the guide and limit stops are very important. Okay. So it will have some failure. I will show you in the next systems and all why the failure occurs in occasional cases. So in this system, there is no failure in occasional case. And one more thing is, for example, if any vertical line is there, if it is running 20 meters or like that, then we have to add proper gate support. So there will be a span for guide supports also. Okay. So if you are not providing guide support, just you provide rest support, what will happen? Failure will happen at this case. Okay, at this location. Because if it is if a line is running 25 meter or 30 meters, so you will apply wind. So definitely there will be a failure in the wind case. So in those cases, what we need to do, I will show you some distillation column lines and all. I will show you why the failure happens in the future videos. Okay. So you have to remember that if failure happens in occasional case, you have to check in which case it is getting failed. For example, if it is failing in X direction, for example, your line is like this. Okay. If your failure is in X direction, like this. Some line is traveling. Okay, so if you observe failure in X direction, what we need to do? We need to add some restraint in X direction. Understood? No? X direction. If you observe failure in Z direction, you have to add failure means support in Z direction, like this. So here, if you observe any failure at this location in Z direction, what we need to do? You need to add limit stop at this location, somewhere in this line. Okay. So like this, you have to think and work accordingly. But if you are doing more projects, then only you will get this experience. Okay. Just I am giving some idea only. So you have to practice well, or you have to work on different systems. Then only you will get more knowledge on the analysis point of view. Basic modeling, it is easy. Okay, if you follow the videos or if you follow the inputs properly, then you will get good knowledge on the modeling point of view. So analysis point of view is very important, because in pipe stress analysis, modeling is around 15 to 20% only, but analysis is a major portion, around 80 to 90% analysis is important, and balance 5 to 10% is for stress report, that I will tell you later. Okay, so now we have checked the stresses in hydro, sustain and occasional. We will check the stresses in expansion case now. So I will change the pressure. Okay, previously 1105, and this one is this. So I will change this one to original parameters. Just pressure. Here it is in 40 bar. Just double click this. You will get edit. In edit you can change maybe how much pressure, I don't know. Previously we took. Maybe 4 bar something. Let's see. Maybe in the Hydrotest 9.15 means 9.15 1.5 times, no? 6.1, maybe 6.1 pressure we are given. Double click this, you can edit here also 6.1, and temperature we didn't change anything. Okay. So now you have to run this batch, do the batch run. Analysis is different. You will have different perspective for different persons. Okay, so result will be different for different stress engineers. Okay, our ultimate aim is to qualify the stresses, and displacements also should be within the allowable, stresses should be within the allowable, and nozzle load should be within the allowable, and support loads also within the allowable. That is our ultimate aim. Okay. Okay, now we will check the stresses in expansion case. So you have to select all the expansion case and stress summary. Select stress summary B report. Now we will see how the stresses has been calculated in expansion case. Expansion case is more critical out of all the stresses. And if you have fatigue, then you need to check the stresses in fatigue cases. So in expansion case, you can see, I'll take this one. So 45.7, 17.9, 14, 12.7%, 27 point. Maximum is 59.7 at note number 430. So maximum stresses is 59.7. It is within the allowable. I will show you when 59.7 has been arrived. What is code stress? 103.1 divided by 172.7, sorry, 103.1 divided by 172.7 into 100. 59.69, that is nothing but 59.7%. Okay, so as per code it is okay. I will show you the code. So in expansion case, you see what is the formula is SE should be lesser than SC. So in interview for freshers, I'm telling freshers or up to 5 years experience, in the interview they lost the questions. What is the formula for calculating stresses in sustained case, hydro, occasional and expansion? You just tell this one, SE should be SE should be lesser than or equal to SC. SC should be lesser than SC. In sustained, SL should be lesser than SH, and occasional SL should be lesser than 1.33 of SH. If you tell that is enough for them, okay, you will have some idea like that, they will think, okay. So for the beginners only I am telling, okay. So this one, SE is liberal, SE is computed displacement stress range, and SCA is allowable displacement stress range. So this is from the code. I took the formula. So SC has been calculated based on root of SA square plus SB square plus 2ST square. Okay, this is for SC. So SC has been calculated based on this formula. Then SA. So here in what we have done for hydro, we took the value from input spreadsheet for the yield strength, and for the sustained and occasional, we took the value of hot allowable stress for the input spreadsheet or from the directly from the table A1 of 31.3, ASME B31.3. But in expansion stress, SA will be calculated based on the formula. So we have a formula for calculating SA. So what is SA is allowable stress only. This is allowable displacement stress range. And as per code, what is the formula? SA equal to F into 1.25 SC plus 0.25 SH. Okay. So here SA we know that is allowable displacement stress range. And what is F? F is stress strain reduction factor. You see, stress strain factor it is given. Okay, this F is always 1 if the number of cycles is lesser than 7,000. Okay, so I have to remember what is number of cycles. Number of cycles means on shutdown again turn on the system, plant. Okay. So if the number of cycle, for example, generally for any project, number of cycles is 7,000. Okay, then your FLA is 1. For onshore project, most of the onshore project, we are using FLA as 1 because the number of cycles is 1. Number of cycles is lesser than 7,000. So how this has been calculated means, for example, per day 1 shutdown and again start means. Per year how much? One cycle per day means into 365 days, 365 cycles. Okay, so 7,000 divided by 365, this is per year. Okay, so we will get 19 years. So if you are using value of F equal to 1, then your design life of the cycle, design life of the plant is 19 years. So generally you will not get 7,000 cycle for onshore plants. Okay, so it will be very lesser than that one only. So your lifetime will be increased. So for example, if you are designing for 20 years, so your plant life cycle will be more than that. If the number of cycles is lesser than 7,000. For example, if number of cycles is 3,500 only, then your lifetime will be double the time. You will get up to 30 years or 35 years that plant may run successfully. Okay. So this F value is very, very important. If the number of cycle is more than 7,000, then your F value will be reduced. Will be 0.9 based on the number of cycles. We have used up to 0.69 for some of the FPSO projects. Their number of cycles is more than 15,000 or 21,000 also sometimes. Okay, so that you need to calculate based on the formula. So F can be calculated using this formula, 6 into n to the power of minus 0.2. Okay. So maximum value is 1.2 for ferrous material. Generally, we'll use 1 only. Don't go for this is for FM. Okay. Maximum value. So we will go only with 1 only. Okay. So now we'll see this F. F is stress strain reduction factor and 1.25 into SC. What is SC is cold allowable stress. Cold allowable stress. I will show you where you will get the value. See, this is for example this one for this particular material, and based on our ambient temperature, this cold allowable stress value has been taken. So here cold allowable stress is 115.146 in this project. Okay, in this project, in this particular system. Okay, and SH already we have seen. No, what is SH? Hot allowable stress. Okay, so based on this formula only, allowable stress has been calculated. This formula is without liberal stress allowable. So this value F into this formula F into 1.25 plus 0.25 SH. Okay, this SH is minimum hot allowable stress. So out of this, for example, in this case 5 allowable stresses we have used, means 5 temperatures only we have used. So out of this 5 temperature, which one is minimum value, that only it will be considered in the calculation of SA. Okay. So this is without liberal stress. Liberal stress means go to environment, special execution parameters. You see, liberal stress allowable for this job. Generally, in most of the project, you should not use liberal stress. Okay. So where it is applicable means when you are doing analysis for the higher temperature lines, for example, above 400 degrees C or above 350 degrees C. If you are doing analysis for power plants like main steam lines, so it will go up to 550 degree, or the refineries if you are doing analysis for reactor lines or any hot oil lines. So there you will have higher temperature. In those cases, what we need to, you need to select this liberal stress allowable and do the analysis. First, we need to do analysis without liberal stress only. If it is qualified, then it is good. If it is not qualified, then you have to use the liberal stress with the approval from the client. Okay. So without approval from the client, don't use the liberal stress. Generally, all stress design basis states that it should not use liberal stress allowable for expansion stress qualification. Okay. So now we'll see. 1 minute. We'll see the result. In expansion stress, select any one case test summary, and value is allowable stress. What we have got is 172.7. So it has been calculated SA equal to 1.25 SC plus 0.25 SH. Okay. So now we will see. I will show you. Already I did some calculation. Let's see. 44.9. What is our percent? 45.7. Okay. So what is F? It is F equal to 1. This is F into 1.25 SC. So 1.25 into SC. What is SC in our case? 115.146. Same thing only. And 0.25 into SH. Again SH. So what is SH in our case? It is 115.146. Same value only. So once you multiply and add this one, you will get 172.6 megapascal. That means 172.7. Okay. So it has been calculated like this one. That is without liberal stress. If you are using liberal stress, your equation will vary. You see, there is a change in equation if you are using liberal stress. With liberal stress. This is F equal to 1.25. 1 minute. I'll just write it down here. The formula for expansion stress calculation in the allowable displacement stress strain calculation with liberal stress is this formula. Okay, this you can try and let me know if the results are okay. Okay, so now I have done the calculation for without liberal stress. You can try this with liberal stress. If you are getting the results, then it is okay. Otherwise, we will do in the next this one video. Okay, which is with liberal stress. So how this equation has been arrived means liberal stress is nothing but SH minus SL. This is a basic formula without liberal stress. So now what happens means they are adding this SH minus SL. So this is liberal stress allowable. Okay, so this they have included this one SH minus SL, then F into 1.25. So if you are adding this one 1.25 SC plus 0.25 SH plus SH minus SL. So I am removing I removed the brackets and I included here. Then you will get 1.25 SC, 0.25 SH plus 1 SH. So if you add these two, you will get 1.25 SH minus SL. So after this 1.25 and 1.25 is common, so I have taken out, and within the bracket SC plus SH you will get this, and minus SL. So like this, so only they arrived this formula for this SC. Okay, so say finally you will get this formula F into 1.25 within the bracket of SC plus SH minus SL. Okay, like this only it has been calculated. You try this one. Okay. So now we will see in different case. I mean, why the failure happens. Before that, I will show you if you change the, I mean, this SH value how it has been taken. Now all SH values are same. Now I am going to change the temperature. For example, 300 degree. Example only. Okay. So T1 300 degree for this one. So I am changing here also. Changing this to 300. So all lines I change to 300 degree. Okay. Now see, if I change this temperature, automatically your hot allowable stress value has been changed. It has been reduced. You see, previously it was 115.146. Now it is 98.077 for 300 degree Fahrenheit. To go to here for 300 degree Fahrenheit, 16.7 only. So for 300 degrees centigrade, not Fahrenheit. Sorry, I was confused. So here 300 degree Fahrenheit means 572. Sorry, degree centigrade 572 Fahrenheit. You have to go to next page for 572. So it should be within the range of this one. Okay, A312 TP 316L. 316L. Okay, yes, 31603. This UNS number is important. A312 TP 316L. So allowable stress value in between 14.8 and 14. Between 14.8 and 14. So allowable stress value is for 500 it is 14.8 and for 600 degree Fahrenheit it is 14.0. So using interpolation formula you will get the exact details. So I am going to use some interpolation formula here. So in the interpolation you see for 500 degrees Fahrenheit the value is 14.8 and for 600 degree Fahrenheit 14. And what is the value we want to know? Ours is 572 degree Fahrenheit. So we have to enter 572. So we'll get the value of 14.224. That is your KSA value, 14.224 KSA. Your allowable stress value is, go to pressure here, 14.2 KSA. That is 97.9 megapascal. You got it? No, it is 98, almost same. Okay. So like this only you have to get the value exact value using interpolation formula. Okay. Now we'll see the result first. Okay, so I'm going to rerun the system. So I enter this value. I change the temperature. Now I'm going to rerun the system. Now you see the expansion stress has been exceeding the allowable limit because it is showing red color. No, 1 minute. You check this. You have to check the stress summary. So in this allowable stress, so you see the allowable stress. Previously it was 172 point something. Now the allowable stress has been changed. 1 minute. So now we will enter the value. We'll calculate the allowable stress for this allowable stress, SA value at note number 190. F is 1, what is SC? SC is same only 115.146. Just I made this formula, okay. And what is SH? It is 98.077, okay. Then you see your allowable stress value, what we got it, 168.45. That is 168.5, okay. So if you change the allowable stress, hot allowable stress, then which one is the minimum value only it will consider, and it will calculate the SC, okay. So don't go for maximum, okay. So, but in sustained case, what happens? It will consider the maximum one. So I will show you now itself. Sustained case, what we have seen previously, what allowable stress is. In sustained case also, you see it has been changed. In sustained, allowable stress has been changed. It is also using the 19 minimum allowable stress value. 1 minute, I will show you in sustained case. In sustain also, previously it was 115.1. Now also, the cases, if you change the allowable stress value, it will show the allowable stress value also change. If you change the temperature, so maximum temperature, the allowable stress value has been reduced. So that value only it is comparing for sustain as well as for the expansion stresses. Okay. So now we will see with liberal stress. What now we will, for example, you take 49 case. 49 case. What is the stress value now? 235.5. This is without liberal stress. Now I will change the temperature as per the original one, 82 degree. Then we'll see the result. I'm going to change the temperature as 82. So now we'll see the result with liberal and without liberal. This is without liberal. I didn't switch on the liberal stress. Sorry. Let's say maximum stress will be for this case because this is expansion range. So expansion, how this expansion has been calculated means based on the temperature response. This allowable stress value for expansion stress range, you will different temperature, different allowable stress if you check. 1 minute. The allowable stress remains same, but how this SC has been calculated is, it is using this one only. What is this case? L2 minus L6. That means L2 minus L6. T1 minus T3. So directly it will take the thermal expansion coefficient. It will have impact on the displacement only. I will show you later that one. Okay. While checking the displacement, I will show you how the displacement has been calculated based on the formula. So now this is with liberal stress, 172.7 is our allowable stress value. .7. Now go to environment, special execution parameters, switch on the liberal stress. Okay, go to the bachelor. Okay, now we can check the stress. See, previously with without liberal stress is allowable stress is 172.7. Now you see it is 277.7. So that means your stresses has been reduced. You see, previously it was 59.7. Now it has been reduced to 37.2. Okay, so this much advantage we have if you are using liberal stress allowable. So don't use this liberal stress and allowable without approval from the client. Okay, unless otherwise it is required, then only you have to use for the higher temperature lines, not for the normal temperature lines. Okay, up to 250 and all it's not required. 250 or 390 degrees C it's not required. Okay, so we'll see why the failure happens in expansion case. Because why the failure happens is because of the rigid routing. If there is no flexibility, then it may fail. Or I'll show you one example. If you don't have proper supports, for example, if a pipe is moving, then if you arrest that movement, then there will be a failure. I will show you with the animation. Just sometimes it may take time. Otherwise, you close this again. You open this output. Yeah. Now it came. You see, this is an animated view of our case. All cases will be there. So if you select sustain, in sustain how the behavior will be. So this is, I mean, it will do exaggerated movement, not the realistic one. So don't get shocked. It will not be like that side. Okay. So in sustain, you see, previously we have seen some failure is there. So previously the movement was there, no, in the downward direction. So we have added a support, so there is no failure. See, there are some, I mean, movement in the downward direction. You see, in this case, so some support is required, maybe in this case. So don't go by this animation. Just for your knowledge only, shown this one. But you have to see. You see, generally, how the movement will be means this is your anchor point. Okay, for equipment, this for pump anchored here. Correct, no? So always your movement will be opposite to the anchor. Like this it is, the movement will be. So here it is anchor. So it is, the pipe is moving in this direction, opposite direction only. Okay. So you have to check properly. So if you arrest this movement, then we'll show how the failure may happen. I will show the result. So do you understand now what is difference between the allowable stress and normal stress? So don't use the allowable stress value. Okay, so So as per the animation what we have observed, your pipe is moving in this direction. So generally you should not give any guide at this location because you should not arrest the movement. So how to add the flexibility means you have to add some elbows, that then it is okay. But you should not arrest. For example, I am just giving one, maybe here one support is there, no? One rest support is there. I am adding one limit stop here, 390 limit stop means in this direction I am arresting the movement. Some people will think in that way. So means if you arrest this one, that movement will be reduced like that. Definitely movement will be reduced. Then we will see the result. Okay, stresses will be increased. You see, previously what is the stress percentage? It has been reduced to 37% after using liberal stress. Now, see, stress ratio is 246.2. It's very high. We'll see in the 3D plot. Okay, first we'll see in the 3D plot where is the failure. At 49 load case, go to overstress point. This is the overstress. Sorry. This is the overstress point. You remove this T. We'll see where is the. You can see the failure at this T. That means your movement is like this. So you are arresting a movement. So your stress concentration will be more at this T locations. Okay, so don't do like that. Okay, you should not arrest the movement or you should not arrest the expansion. For example, any pipe rack line is there like this, some 100 meters it is running or 200 meters, anything. Okay, so don't give guide support immediately after the elbows. So don't try to give guide support. Some 2 to 3 supports you leave. After that you provide guide because your pipe will tend to move in this direction. Okay, so you should not arrest the movement. So if you want to arrest the movement, add elbow, add elbow or add expansion loop. I will tell you where to add expansion loop, why to add expansion loop on the. Okay, we'll discuss later. So here the failure is here only because of this limit stop. So you should understand the cause of failure. Okay. So now we'll remove the limit stop. Okay, so I am going to remove the limit stop. I will show you some other example. So now what we have done, we have checked only the stresses. What are all the points to be checked for the stresses output? We need to check. 1 minute, I will go to the first page. One is stress. 1 minute, I will reopen this. Okay, first is stresses. Now we have checked the stresses. Then we need to check displacement, that we will see in the next video, and restraint summary or pipe support loss. Then nozzle loads. So already we have seen the flange linkage check. Anyway, we will see Tunian check also we have seen already. So now we need to check the displacement, restraint summary, and nozzle loads. Okay. I'll show you some example. Okay, this is one of the files we have done the analysis. This is for one small skid. So most of the skids, they used to provide support, I mean U-bolt support only. So U-bolt support means you need to add a hold down, guide and rest. I will tell you what is U-bolt support and what is hold down support. Support engineering I will explain you later. You see, stresses are exceeding the limit. We'll see how to qualify the stresses. So double click this ratio. Where is the maximum stress? Yeah. See, at this location stresses are exceeding. What we'll do, we have copied and we'll paste at this location. So we need to do like this, then only all stresses will be clear. You see, at node number 10,800, go to 10,800. Okay, this is a typical failure in. Always you will find failure at this location. Mostly for PSV inlet line, you will find a failure. Wherever the reducer and flanges are, no, this location. So what we need to do means, if any failure is, first we need to check the movement. Because what causes failure? Our anchor is in at this location. So what I told you, always opposite to the anchor only your pipe will move. Pipe will move in upward direction as well as in the downward direction. So here our equipment is anchored at this point. Oh, so at this point means pipe will move in the upward direction. Pipe will move in this direction only. Okay. So you should not harass this movement. So they have given some hold down support here, and also so we will see one by one. First is 10,800 and then 10,510. So for this general, I told you know in the PSV inlet, if any failure is there, for example, sorry. So for example, if you have failure here, generally what we do after the reducer, okay, introduce one spool. So 100 mm spool you can introduce. After that, you add the flange. Okay, then your stresses will reduce for the expansion case. This is a general practice. Okay, if 100 mm is not sufficient, then you have to increase the spool to 200. Okay, like that, but with the approval of from the process team. So you need to get the approval from the process team regarding this, and also with the layout team. Okay. And next node number is 10,510. 10,510. Same another PSV this side. So then at node number 520. 520. Okay, you see here some failure is there at this location. We will see why the failure is happening at 520. So now we will go to the animation. We will see why the failure is happening. Here we will see the 3D plot. First we will see the 3D plot. What is the movement and where the overstress points are. So So select expansion case, 49 case, and overstress. So wherever it's showing red color, there are no stresses or exceeding. So there are a lot of locations. So I'll switch on the flanges. Also, let's see here. This portion is overstress. I will tell you why this portion is getting overstressed, and see these points are overstressed. These two locations here, here, then here. Where are the other points? We have seen at this T, the PSV inlet. Okay, we'll see. So this calculation already we have solved. So I know what is the problem here. Okay, I will show you. First, we'll see the deflected shape, how the pipe is moving. Or if you want to see groove means, you can see the groove. Okay. So first we will focus on the failure locations. At this point, you see, our anchor is here. This equipment, this is one of the pump. So this is anchor. Here they have provided anchor. What happens? Your pipe is moving like this and it is going down. So your movement is in downward direction. So what they have done, they have added on support at this location. Means they are arresting this movement. They are arresting, means like this, they arrested this movement. So what happened means pipe, it is going away from this. Okay, so what they have to do, they have to remove the support, or they have to provide gap for this support, or they have to move the support towards this location. Okay, and your pipe is moving in this direction, you see, means your expansion is towards this direction. We have to see here why the pipe is moving is this direction. You see the pipe is moving also in this direction. Why? Because you see, I told you, no, any direction change, don't provide support, don't provide guide support. If any direction change is there, don't provide guide support on the direction changes. So here this support is causing failure here also and here also. Okay, so we will try to remove the guide support here. If you remove the guide support, definitely it will pass, I think so. Yeah, we'll see. We'll remove the guide support first here, and here also we'll remove the guide support. Then this failure will reduce. And for this location, we will see this location also failure is there. So see, your pipe is moving up. So they were arrested here, you see, they arrested this movement. So what we'll do, we'll remove this hold on support, this support alone. This support will remove. Okay. So hold on support is nothing but vertical support only, like this. If any shoe is there, like this. So this is the hold on. So it will not allow the pipe to move up and down. Okay. I will show you in the support standard what is hold on support. Okay. So now we'll concentrate on this 4 location, then we'll see. If you want to see the animation, you can see the animation. you check the maximum design temperature. In the animation you will not get expansion case, so you check the maximum design. See this. This is not a real one. Okay, we will reduce the you press this one, then your movement will be reduced, it will be slowed down. So our failure is at this location. So whatever we see, no, the deflected shape, the same thing only it's happening here. So it is moving in this direction, so we need to remove the guides. And for the PSV, you can see our anchor is at the bottom, so the pipe is moving towards up. You see here also it's moving towards up. So we'll see, we'll remove the hold down support there. We'll see the results. Okay. So we'll remove guide here. If I just entering stiffness as 0 means it will consider the support is not valid there. Okay, means if like this, if you just give 0 or point anything, it will be invalid. Well, the support will be deleted. Like that, if you give 0, then if you give stiffness as 0, then the support is not there. So just I am removing the support like this, 0. So I remove the guides, and in this location we need to see we need to remove this one. I'm going to give plus y. I removed minus y. Okay. And also we'll try to provide gap for this supports in Z direction. 3 mm gap. Just I'm giving 3 mm gap. And for this direction also we can provide 3 mm gap. We'll see whether this will help or not. And what about these pipes? Yeah, so it was coming down. We'll see, we'll try to remove the support. First we'll see, we have removed 2 guides and hold down support. Still failure is there, but we'll see the stresses. Ratio, double click the ratio. See, still failure is there, but the stresses has been reduced. So at node number 10,800, the stress ratio is 335 previously. Now at 10,800 you can see the stress percentage has been reduced to 116.3, but still failure is there. So you see why the failure happens, because of the wrong placement of guide support. And at node 10510 previously 253%, now it is 121.7%. Okay, so like this you need to check each and everything, and you have to add flexibility, or if unnecessary guides or limit stop over there, you need to remove the support accordingly. Okay, We will see at node 10.5.10. We will try to qualify the stresses at node number 10.5.10. Okay, and 10,800. Oh, same here only. Okay, okay. And 870 at node number 870. That is 870. Okay, here. Okay. And due to improper, imbalance support, the supports was not balanced, then also it may cause failure. Okay, it may cause failure. So we'll see at 10.5.10. 10.5.10. So now we will try to add, or we'll try to provide gap here, or we will add the 10 mm I told or 100 mm here. So I'm going to, what is the weight? 11.7. So what we have observed previously at this location means, so first we'll try this one, and I will tell you the real story of this system 10805. I'm going to break this element. So how to add the spool? Just broken that one. Just added 10 mm spool. Okay, here. So I'll make it as 100. The same thing you have to reduce here. Okay. Whatever we added, it has been reduced. So overall length should remain same. Again, I'm going to break this. Okay, 10. The 10 also we have to add. 10 mm no already. So the 10 mm we have to add it here. So here I'm going to change it this one as 100. And here 100 we have to change this one to 215. Now we will see the result again. Batch run. You see, all the stresses have been cleared. Only the failure at some other locations only. Stresses. Double click the stress ratio. And you see, stresses has been reduced. Whatever we have noted, no? Those locations, we don't have failure. And we have failure at 870, node number 870 only. And at 520, we have some failure. We'll see how to qualify that one. See, 870 and 520, we didn't concentrate. Now we will see how to qualify. So you have to go one by one. Then only you can clear the system very easily. Otherwise, no, it will be difficult if you are concentrating on more points. One or 2 points or 2 locations you can concentrate. So at node number 870, go to 870. So here also, we'll see why the failure is happened. And then node number 509. So you see, if the odd number are coming 519. 519 means there will not be such number. If you search this one 519, you will not find any node number, because 519 is maybe at some elbows. So that means it should be 520. Okay, so you see 519 is the midpoint of this elbow. Okay, you will not find that node number. So now the failure is at this location. Only here, this area only failure is there. Okay. So we'll see why the failure happened here and here. Yeah, correct, no? Yes. Both the elbows failure is there. That means still you have the movement at this location. Sorry. The pipe is moving in this direction. So already we have removed. And okay, I understood. And also this pipe may move in this direction. That will cause failure here. So for that only we have added this elbow. You can see, no? So now what we have to do? We need to increase this spool because we have to add flexibility for this one. So I am going to increase this spool. I'm going to add some 200 mm here, 200 plus. And if you add 200 mm, you need to add here also 200 mm, and you need to reduce 200 mm here because this overall length should remain same. Only we have increased this loop. Okay. Now we will see the result. Run the system. So like this, you have to think. So based on your experience only, you will get this one. Okay. So immediately you will not get this. So you have to work for different system and different project with different temperatures and different materials. Then only you will get the experience of analysis. So analysis concepts remain same only, but you have to think hard. Then only you will get this one. So now you see, previously what is the percentage? Now the same location only, I am going to copy this. Just for our comparison, I am pasting this one because previously at 870, 116% was there. Now at 870, it is very less. I think there is no such node number, so it may be less. And at 519, the percentage is 99.4 previously. Now it has been increased to 102. We will see how to qualify that one. So at node number 520, it means here. So we will see the movement at this location. Go to 3D plot and then expansion case and see the deflected shape. Okay. I see both are same only. So it is expanding like this, and maybe your horizontal direction there are more movement. That means this leg is not enough. So we need to add some more leg, or yeah. And also we need to try to remove this hold on support because but it is not causing failure here. Or we try to add one support here. Okay, yeah, because you see it is imbalance. This is moving up. It is like here. So we'll try to add one support here. Just one valve is there. And here also we'll try to remove this hold down. because it is going down. If we are adding all down, then it's having issue. So we'll remove this all down, and very close two supports are there. So I'm going to remove one support here, and we'll add one more support because this is this 2-inch valve only. Okay, anyway, well, I'm going to add one support here. 315, 150. We'll add one support. Now we will see what will be the result. So like this, some system it will take more time for us. But 519, it is 103.2. The same percentage only, so it was not helping. That support was not helping. We added one rest support, no? So that was not helping because it's 1 or not 2% only. The same 1 or 2%. So what we will do, we will here you see like what we have done for the PSV lines. We'll try to add spool after the reducer. Okay, maybe it may cause failure. So I'm going to add 100 mm here. I'm going to reduce that spool because the overall length remains same, 106. Okay. So now just run the system. So you should not use liberal stress for this system because the temperature is 82 degree only. Yeah, you see, now the stresses has been cleared. Stresses. See, the stresses has been reduced to 87.8. So that is well, it is okay. Below 90% means it's okay. The two without liberal stress means it is good. Okay. So now if you go to this 3D plot, you won't find any overstress point. You see, if you select this overstress, it will show no overstress point or no allowables. Okay, that means the system is safe as far as stress concerned. Okay, then we have to check the displacement, nozzle loads, and support loads. Okay. So like this, you need to analyze. You have to spend time. Then only you'll get this one. Okay. If you understand the concept, then it will be easy for you to qualify the systems, or you find the solution very easily. Okay. I think we will see the displacement and other points in the next video. Thank you very much.